Hello and welcome to Lecture 4 of Work and Energy in Electrostatics in Phys 1204. I hope you're ready for integration because it's time to look at continuous charge distributions again. So we're going to start, as we did with fields, with the simplest continuous charge distribution we can, a uniformly charged thin rod. And the process is going to be very, very similar to what we did for a field, and so I'm going to go through it a little faster. But this is going to be a little bit simpler than it was to find the field at a point P due to this rod, because unlike the field, the potential is a nice, simple scalar function. So, just as we did before, we're going to think of splitting the rod into little bits. And so I'm going to define a little bit of the rod here, which I'll call delta Q, which is also what I'm saying is the symbol for how much charge is on it. And I'll say it has some length, which since it's along the y-axis, I'll call delta Y. And it is at some location in my axes, defined by yi. And finally, I'm going to want to think about the distance RIP. One thing I will say before I go any farther is that I won't need to deal with the vector RIP at all, because this is a scalar function and I won't have to deal with taking any components. So what I'm now going to do is say that the potential at P due to this little piece of rod, so I'll call it delta VI, is going to come from the expression we use for a point charge, and it's only approximate because this isn't actually a point charge, and so it is K delta Q over RIP. So as with the field, I can say that there is some uniform charge density, linear charge density lambda, which is just Q over L, and I can express delta Q as just lambda delta Y. And RIP just comes from Pythagorean theorem. It's going to be root x squared plus yi squared. At which point I can put the whole thing together into my potential due to one piece of the rod. Now I'll build the integral. So the total potential at point P will be approximately the sum of all the potentials due to the individual bits delta VI. And so that is just a sum over I. But I can now do the usual trick and convert that into an integral, which will make it precise. And I'll note that the k lambda are constants, which I'll pull out in front. And so I have, whereas usual, the quantity with the delta on it has wound up as the thing that I am integrating with respect to, because what I have done here is take the limit as delta y goes to 0. And all the I subscripts have disappeared because that's no longer a discrete variable, it's a continuous one. And again, I need to worry about what I'm integrating from and to. I'm going from y equals negative L over 2 to L over 2. Well, again, this is an integral that could be done by trig substitution, but I'm just going to throw it into Maple, and there it is in Maple. That's a rather icky-looking expression, but I hope you appreciate that the process here was somewhat simpler than what we had to go through for an E-field. No R hat vector to deal with, we didn't have to worry about components and which ones might cancel out and be 0. We could just go set up a simple integral, and look it up or use Maple. Let's just check units to make sure. This is all a length plus a length over a length plus a length, and so this is unitless, and so all we have is k lambda, which is Newton meter squared per Coulomb squared, times coulombs per meter. And so that's Newton meters per Coulomb, which is joules per Coulomb, which is volts. Well, let's do the uniformly charged thin ring again. So here is the geometry, and we're going to have exactly the same definition for delta Qi that we had when we did the field. We can define some little delta theta, and in radians then, if delta Qi is lambda times that arc length, then it's lambda r delta theta I. And once again, this RIP is going to be the square root of z squared plus r squared, just as it was before. And so that gives us our potential due to one bit of the rod. I'm going to skip straight to writing the integral. So my potential at P is going to be, I have constants k lambda r, and everything in the denominator is a constant as well. We're not integrating with respect to z or r. And so we have the easiest integral ever, and we are integrating theta from 0 to 2 pi, in other words, all the way around the ring. And so that's pretty simple. That integral comes out as nothing more than 2 pi. I could now go through the very long process of using this to get the potential due to a disk, and then let r go to infinity and get the potential due to a plane. But in the next video lecture, we're going to see a much easier way to do that.